So today our lesson is going to involve divisibility rules. Previously we did basic. Today we're going to take a look at advanced. When we started out the basic session last time, one of the things I pointed out was that vocabulary is extremely important when dealing with all of mathematics and with divisibility rules in particular. And during that last session, I talked extensively about divisibility. What I want to do is make a connection now between that and the word factor. So in the gray box there, a vocabulary note says, when a number A is divides evenly into another number B, we say that A is a factor of B. So without all the A's and B's, let's take a look at what that really means. So 7 does not divide evenly into 12, so 7 is not a factor. So when one number divides evenly into another, then we have a factor situation. So I'll be using the word factor quite a bit today, so I want to make sure that that is very clear. Okay, so in our last session, we looked at divisibility rules for 7 different numbers, and today I'd like to review those as a jumping off point for the advanced rules that I'll be presenting a little bit later. So we started with divisibility rules for 2, 4, and 8, and came across something very interesting. I grouped these together because the rules for these have something very strong in common. So let me get something on my whiteboard here. And let's go with the number 7,848. And the question is, can that number be divided first by 2, then by 4, and finally by 8? So the rule for 2 is we're to look at the last digit and see if it's even. And in this case, it certainly is. So 2 is a factor of 7,848. We don't have to do the division. We can just, in this case, look at the last digit. Now, the rule for 4 is similar, but just a bit more expansive. With 2, we look at the last digit. For 4, we look at the last 2 digits. And we think back to our times tables. Does 4 go into 48? Well, yeah, because 12 times 4 is 48. So 4 goes in. Or, if you weren't sure about that, if you didn't remember your 12s tables, a really good strategy for dividing by 4 is to take half of a half. So if we took half of 48, that would be 24, and half of 24 is 12. So, yep, 4 definitely goes in. Now the rule for 8, it takes this idea and expands it out yet one more place, and we look at the last 3 digits. So for 848, well, I think the cleanest way to do this is going with half of a half of a half for 8. So let's find first half of 848. Half of 8 is 4, 2, 4. So we could do it once. 2, 1, 2. We can do it twice. And half of 212 is 106. So yep, we could cut it in half 3 times, and so that means that 8 is also a factor here. So that takes is the strategies for 2, 4, and 8. Let's move on to the strategies for 3 and 9. This will turn out to be one of the most useful tools you'll have in your toolbox, by the way. You'll be using this all the time. And for this, let's go with, well, first of all, let's review the rules here. A number is divisible by 3 if the sum of the digits is divisible by 3. And the rule for 9 is virtually identical. The number is divisible by 9 if the sum of the digits is divisible by 9. So let's take a look at this example. Let me make that a little bit bigger there. 5, 4, 6, 2. And our strategy for 3 says to add up the digits. So, oops, if we take 5 plus 4 plus 6 plus 2, so we've got 9, 15, 17. And turns out that 3 does not go into 17, and 9 does not go into 17, so neither of those numbers will go into this particular number here. However, let's do one where the divisibility actually works. I'll use a very similar number. Let's use 6, 4, 2, 6. And again, if we add the digits here, 6 plus 4 is 10, plus 2 is 12, plus 6 is, this time we get 18. And both 3 goes into 18 and 9 goes into 18. So this number is divisible by both. So this is a bit of a change from the previous one where we looked at the last digit, the last 2 digits, the last 3 digits. This time, The strategy for 3 and 9 is to add up the digits and see if the number goes in, that is to say, is it a factor? And the last rules that we looked at the other day were the rules for 5 and 10. For most of you, I'm pretty sure this was a number that most of you knew right off the top of your heads, but let's go through it for completeness and clarity. So the rule for 5 is the number must end with a 0 or a 5. After all, when we count by 5s, 5, 10, 15, 20, 25, then all those multiples of 5 always end with either a 0 or a 5. Okay, and for 10, pretty straightforward strategy. If the last digit is a 0, 10 is a factor. So that's about the cleanest rule that we have. So let's take a look at an example here to round this out. So 2009-60, is that divisible by 5? Certainly, because it ends with a 0. Is it divisible by 10? Certainly, again, because it ends with a 0. But what if I changed it to this? And ask the same question, is this number divisible by 5 or is it divisible by 10? Well, this time the ones digit, the last digit, is a 5, which means that 5 goes into it. But it's not a 0, so 10 does not. So in this, for here, both 5 and 10 go in. For here, just 5. And that'll happen from time to time. Okay, now, divisibility rules advanced. Let's take a look at, well, as I said, this is advanced, and so I'm going to be introducing you now to a pretty high-powered tool that math people use quite a bit. And the phrase that I'm going to introduce is the relatively prime. Now, I'm sure at this point in your education you've run across prime numbers, those numbers that cannot be divided by anything except 1 in themselves. And also you probably know that the first prime number is 2. After all, what goes into 2? Well, 1 and 2, 1 and itself. 2 different numbers, and 2 and only 2. There's another class of numbers that we call relatively prime. And let's take a look at what this means. So the numbers 8 and 9, neither of those numbers are prime. In fact, if we look at the factors for 8, they're 1, 2, 4, and 8. And the factors of 9 are 1, 3, and 9. So what does relatively prime mean in this context? Well, when 2 or more numbers are relatively prime, if they have no common factors other than 1. So check it out. 8, these are the factors, and the only one they have in common is the one in red, and that's the 1. So that means that 8 and 9 are relatively prime. That is, they have no common factors other than 1. And interestingly, there's no requirement that either number be itself prime. Let's take an example of a case of 2 numbers that are not relatively prime, 12 and 15. So the factors of 12 are listed here, and the factors of 15 here. And as we can see in red, they have a common factor of 1, which in fact every number has a common factor of 1, and they have a common factor of 3. Well, to be relatively prime, they can only have a common factor of 1, so 12 and 15 are not relatively prime. So we're going to be using this in context, and if this is a little bit vague at this point, that's okay, but we'll get that cleared up before the end of this lesson today. Okay, so what we're going to do now is use this idea of relatively prime to help us know when some numbers that are bigger than we've been using so far are actually factors of the given number. So the compound divisibility rules say if 2 or more numbers that are factors of a given number are relatively prime, then their product is a factor as well. So let's do an English translation of that. And on my whiteboard, let me get that number down. Okay, so whiteboard, please. There we go. Okay, so let's take a look at this. And question, is 4 a factor of this number? Yes or no? Pop that in the chat box. I haven't been looking much at the chat box until right now. Is 4 a factor? And let's add one more. Is 5 a factor here? Well, we have divisibility rules for both 4 and 5. So, yay or nay? Is 4 a factor? Is 5 a factor? Oops. And what we see here Well, for 4, the rule for 4 is the last 2 digits, and 4 certainly goes into 40. So 4 is a factor. And I asked about 5 as well, and this number ends with a 0, so 5 is a factor. So let's take a look at these two factors now. Are they relatively prime? That is the biggest number, the only common factor they have 1? Well, let's see. What are the factors of 4? Those are 1, 2, and 4. And what are the factors of 5? Those are 1 and 5. And indeed, the only common factor they have is 1. And what that means, according to our theorem, let me go put that back on the screen here, is that 4 times 5 is also a factor. So that's what this has been leading up to. If we can find 2 factors that are relatively prime, then their product is going to be a factor of the original number. So looking at that number again, the 2006-40, 5 and 10 are also factors. In fact, let me get that on the whiteboard here. 2640. Okay. And it's obvious that 5 is a factor. It's also obvious that 10 is a factor. So 5 because it ends with a 0, 10 because it ends with a 0. Now, big question here. Are 5 and 10 relatively prime? That is, do they have any common factors other than 1? And immediately we can see that indeed they do have a common factor other than 1. The factors of 5 are 1 and 5. And the factors of 10 are 1, 2, and 5. So what we have here is a common factor of 1, also a common factor of 5. So these numbers are not relatively prime. So 5 times 10, 50, does not go into 2,640. By the way, we can also see that right off the top because the last, well, we'll get into that a little bit later. Okay, so let's take a look now at this example. Given that 360 is divisible by 5, 6, and 9, name 2 other factors and one number that is not a factor based on this given information. Okay, so let's do this in parts. Let's go for first for 2 numbers that divide 360, that we can use 5, 6, and 9 as our guideposts for it. So any thoughts on this? Again, I'll wait to let the chat box catch up with reality here. Okay. Seems to be running a little bit on the slow side today, a little slower than usual. Sorry about that. Okay. Well, let's see. Okay, I see 36 as an answer. I'm not quite sure where that came from. Okay, 2, 4, and not 8. Okay, good, Giselle. How about using it says, given the fact that 360 is divisible by 5, 6, and 9. So let's use that relatively prime idea. Are 5 and 6, are they relatively prime, yes or no? Well, when you think of the factors of 5, they're 1 and 5, and 6 is 1, 2, 3, and 6. So the only common factor they have is 1. So 5 times 6 will also be a factor of 360. So 360. Let me see. 5 and 6 work. Okay, are there any other, between those 3 numbers, are there any other 2 that are relatively prime? Not 7. Okay, we'll get to the rule for 7 in a little bit. Okay, and if we look at those numbers, 5, 6, and 9, 5 and 9 are also both relatively prime because the only common factor, again, disqualifies them from being relatively prime. So 6 times 9, 54, is not a factor of 360 in this case. So this compound rules is going to help us be able to generate a lot of factors of numbers based on finding some of these small numbers and then compounding them to make larger factors. And with that in mind, what I'd like to do is go on to the new specific divisibility rules for today. And the first one is 6. A number is divisible by 6 if it is divisible by both 2 and 3. So let's quickly review the rules for 2 and 3. 2 was the last digit, and 3 was the sum of the digits. So if both of those things are true in a given number, then the number is divisible by 6. The first example there, 792, is divisible by 6 because it's divisible by 2, because it ends with an even digit, and it's divisible by 3 because it adds up to 18, which is divisible by 3. So this compounding immediately gives us a very useful rule here in 6, which is a number that we'll be using quite a bit. How about 634? Well, 634 is not divisible by 6 because while it is divisible by 2, it ends with an even digit, it's not divisible by 3. Because when you add up the digits, 6 plus 3 is 9, plus 4 is 13, and 13 is not divisible by 3. Okay, so quick exercise here. Which of these numbers are divisible by 6? I'm going to give you guys a minute to pop those answers into the chat box, if you would be so kind. And let's see what we get for these. Again, the question is, which of these 4 numbers are divisible by 6? And I'll be right back on screen. Okay, and seeing 936, which is correct. How about the first one there, 25, 29? Well, can't be divisible by 6 because, first of all, it's not an even number. So if the 2 rule doesn't work, then immediately we don't have to go any further. How about 704? Let's see. Well, it does end with an even digit, so it's divisible by 2. But when we add the digits, it adds up to 11, which is not divisible by 3. So the 704 will not be divisible by 6. And as a couple of folks have correctly said, 1002 definitely is divisible by 6. It ends with an even digit, and it sums to 3, which is divisible by 3. So our rule for 6 is based on the previous 2 rules we've learned of 2 and 3. Now we're going to do a similar thing when we move on to the divisibility rule for 12. And a number is divisible by 12 if it's divisible by both 3 and 4. And note, as it does on the screen, that 3 and 4 are both, 3 and 4 are relatively prime. So looking at the examples there, 1560 is divisible by 12 because it's divisible by 3. The sum of the digits is 12, and that's divisible by 3, and it's divisible by 4. Recall the rule for 4 being, does 4 go into the last 2 digits? And half of 60 is 30, half of 30 is 15, so yep, we can take half of a half, and we're done with that. How about 942? Well, not divisible by 12 because, yeah, add up the digits, and it is divisible by 3. But unfortunately, 4 does not go into the last 2 digits, which are 42. So the rule for 12 is very similar to the rule for 3. Find 2 relatively prime numbers, and under those conditions, it will work. So let's apply that to these 4 numbers down below. And again, please tell me which of these numbers are divisible by 12. That's a lot of good answers to the last question. Let's have some folks get in the chat box and let us know which of these numbers are divisible by 12. Okay, 624, indeed. Whoops. And thumbs up on that is true. It's good. What else? How about 836? Is that divisible? Well, let's see. By 12, we need it to work by 3 and by 4. 8 plus 3 is 11, plus 6 is 17. So 3 will not go into 17, so 836 does not work. How about 372? Okay, got a couple of folks chiming in with 372. Let's check that. Yep, it's an even number. Oh, excuse me. We got to look at the last 2 digits here. So 74, is that divisible by 4? This is going to be a little harder to do mentally, but half of 72 is 36, and half of 36 is 18. So yeah, 4 goes in, and let's check the rule for 3. 3 plus 7 is 10, plus 2 is 12. Yep, 3 goes in, 4 goes in, so definitely 12 does as well. And finally, the last number here, 6,000. Nobody's mentioned 6,000 so far. There we go. Thank you, Faith. 6,000 will definitely work. The sum of the digits is 6, which is divisible by 3, so that takes care of the 3 requirement. And does 4 go into the last 2 digits? Well, 4 goes into 0 times. So, yep, 3 and 4 both go in. So our rule for 12 holds up for, turns out, for all 4 of these except 836. So let's recap what we've just seen here. The rule for 6 is divisibility by 2 and 3. And the divisibility rule for 12 is divisibility by 3 and 4. By the way, there's another combination of numbers that make 12 that we got to be a little bit careful here, and those numbers are 6 and 2. And the problem with 6 and 2 is that they are not relatively prime. They have a common factor of 2. So when you're looking for numbers to consider, please make sure the numbers are relatively prime. That is, the only common factor they have is 1. Okay, now we're going to go on to something that a lot of folks find a bit esoteric, because the procedure here is very different from anything we've done before. It turns out to be an incredibly powerful tool, so it's worth taking the time today to see what's going on here with this divisibility rule, first for 7, and then we're going to apply it to a couple of other numbers as well. So let me read it first. A number is divisible by 7 if, and this is where things are a little different than we're accustomed to, if 5 times the ones digit added to the other digits is divisible by 7. And I think, again, an English translation of this is probably going to be helpful. So let me do a whiteboard demonstration here. Okay, let's get over to the whiteboard. Okay, so the number here is, I want to know if 7 goes into 182. And so the directions tell me to multiply 5 times the ones digit. So I'm going to cut off that ones digit here and multiply it by 5. Well, 5 times 2, of course, is 10. So directions say 5 times the ones digit added to the other digits. So the other digits in this case are 18. So 5 times 2 is 10. We add that up. And the question now is, does 7 go into 28? Well, obviously it does. It goes 4 times. So 7 is a factor of 182. As I said, this procedure looks very strange because it's unlike anything we've done up to this point. But it's a very straightforward process, and the rule never changes, which is the beautiful thing about this. So again, let me say the entire procedure. Let's take it all the way from the top again. Okay, the number I want to know is 182 divisible by 7. So the strategy, multiply the ones digit by 5. 5 times 2 is 10. Add it to the other digits and see what we get. Let's do that again, this time with 213, and see what happens. Well, I want to know if 7 goes into here, so I'm going to multiply the ones digit by 5 and add it to what's in front. And this time I get 36. Is 36 divisible by 7? Well, it's certainly not, because 35 is divisible by 7, but not 36. So 182 was divisible by 7. 213 is not. So, as I say, this strategy is going to take a little bit of time for you to get used to. But once you do, you'll have a tremendous power tool on your hands here that will let you look at certain numbers and just know immediately whether they have factors or not. So, let's go back to our sheet here. Let's see, which of these numbers, 343, these 4 numbers down below, which of those are divisible by 7? So a lot of great answers to the last question. Let's see how this one goes now. Okay, let's take a look at these numbers one at a time. After you've done this a few times, by the way, you'll be able to, I'm pretty sure you're going to be able to handle a lot of these mentally. Okay, but let's do this complete demonstration here. The first number there was 343. as I said earlier, the strategy for divisibility by 7 never changes. All you have to do, straightforward process, multiply the ones digit by 5, add that answer to what's in front, and in this case, ask yourself, does 7 go into 49? Which of course it does. So indeed, 7 is a factor of 343. Now the next number, let's see how that works. That number is 361. Again, strategy, let's go 1 times 5, add it to what's in front. This time we get 41. And since 41 is not divisible by 7, 361 is also not divisible by 7. So every time you see this, I'm hoping you're getting a little more comfortable with this procedure, because we're going to be using it not only for 7, but basically the same procedure for a number of other numbers. Okay, the next number that we had was 704. So I think you're starting to get the idea here now. Anybody have 704 as one of their choices here? Let's see, not yet. Okay, so again, procedure, multiply ones digit by 5, add it up. 7 does not go into 90, it does go into 91, but not into 90, so 704 is also not divisible by 7. Ah, Faye, you said 6006 is divisible by 7, and indeed it is, and it's kind of an interesting one too. Let me get that on the board here. 6006. Notice, by the way, it doesn't matter whether it's an even number of digits or an odd number of digits. The procedure is always the same. Multiply by 5. In this case, we get 630. And so 630, is that divisible by 7? Well, 63 is divisible by 7, and 0 is divisible by 7. So yes, 630 is divisible by 7, so 6006, as you correctly said, Faye, is absolutely correct. So the strategy for 7, strange but not difficult. In fact, pretty straightforward once you've heard it a few times. And something that I think that will help to reinforce the procedure is we're going to go on now to the divisibility rule for 13. And the divisibility rule for 13 is remarkably similar to the divisibility rule for 7, with one exception: the number we multiply by. Let's take a look at the directions here. Let me get you back to that page. A number is divisible by 13 if 4 times the ones digit added to the other digits is divisible by 13. So this is exactly the same procedure we just used for 7, except instead of multiplying by 5, as we did for 7, we're going to multiply by 4. So let's do that. And 2 times 4 is 8. 18 plus 8 is 26. Hey, 26 is 213, so yeah, 26 is divisible by 13, so 182 is also divisible by 13. As always, let's take a look at a counterexample here where it doesn't work. And in this case, at number 213. Okay, someone tell me please, what am I going to multiply by this time? I want to know if this number is divisible by 13. So I'll wait here. Somebody pop that in the chat box for me, please. I want to know if 213 is divisible by 13. So our rule tells us to multiply, and what does it tell us to multiply by? Ah, good. So, couldn't quite pronounce the name, but 4 is correct. So 4 times 3 is 12. Add that up. We get 33. 33 is not divisible by 13, so our original number 213 also is not divisible by 13. Okay, let's take a quick run through these 4 examples here. How about 363? Is that divisible by 13? Well, let's see. Multiply the ones digit by 4. And 48 is not divisible by 13, so 363 is not. How about the other 3 numbers there? I've done 1. How about, okay, I see a no there, but I don't see no to what? 213, we're back in the last one, okay. Okay, well, let's tell you what, let's work out 455 here. So procedure never changes. Multiply the ones digit by the appropriate number. Add it to what's in front. Now, is 65 divisible by 13? Well, you know, some folks are not going to be sure about that. And so one of the very, very extra cool things about this procedure is that if we get a number after we've done the procedure that we're not sure whether or not things are going to work, what we can do is we can do the same procedure over again. So I'm going to take the 65, multiply the ones digit again by 4. 4 times 5 is 20. Add it on to what's in front. This time I get 26. And the question was, is the original number divisible by 13? So the question now is 26 divisible by 13? And after doing this twice, it's much easier to see that yes, indeed, 13 goes into 26, it goes twice. So sometimes you're going to get a number after you do the first step that you're not going to be sure about. Not quite that. Maybe you could work it out in longhand or something. Do the procedure again. Math people call this recursive. You don't have to know that word as much as the idea that you can apply the same procedure all over again until you get a number that works for you. Okay, that takes care of the second number there. How about, let's see, 1001? Okay, let's do our multiply the ones digit by 4. Going to get 104. And again, I'm not sure whether 13 goes into 104. So let's do it again. Apply the same procedure with the new number that we generated here. Hey, again, we get 26, which we just said was divisible by 13. So 1001 is also divisible by 13. And again, this idea of doing the procedure, getting a number we're not sure of, doing it again, and now we're sure. And finally, we have one last number there, 845. And what's the status of that? Okay. 845. Whoa, this number is going to get us 20. 104. And again, that number is pretty big, so let's switch it off, do the procedure again. Interesting that all of these numbers resolve to 26, and so 845 is also divisible by 13. That is to say, 13 is a factor of 845. So the rules for 7 and 13 are very similar. We saw that the rules for 2, 4, and 8 kind of formed a group, and the rules for 7 and 13 kind of do as well, because what we're doing is we're multiplying the ones digit by something specific, adding it on to what's in front, and then seeing if our number in question goes into that number. That is it a factor? Now, I have one more number I'd like to show you divisibility rules for today, and this turns out to be not only useful. There we go. The best divisibility rule for 11. There's a parenthetical note there that says, for more rules on 11, download today's practice PDF in the comments below. There are actually 4 different rules for 11 that we talk about. We don't have time today to go into all 4 of them. So I picked what I consider to be the best of these rules. And this rule is so straightforward that it's kind of startling, actually, that it works. But, well, let's see this in action. So a number is divisible by 11 if the rest of the digits minus the ones digit is divisible by 11. So when you take a look at the number 407, off the top of your head, you know that's not divisible by 2, by 4, by 5, by 10. Is it divisible by 11? Well, the rule says to take the rest of the digits, that in this case would be the 40, minus the ones digit. 40 minus 7 is 33, which is divisible by 11. See how straightforward that is? 40 minus 7 33, and that gives us a number that is divisible by 11. The counterexample there, the 841, again, subtract the ones digit from what's in front, and you get 83, and 83 is not divisible by 11. So boom, we know that 841 is not either. So sometimes looking at certain numbers, you can be able just to look at it and go, oh, that's divisible by. And well, let's take a look at the four choices down below there. The 187, that's going to be 18 minus 7, which is 11, which is divisible by 11. So at 187, 11 is a factor. How about 526? Well, it's going to be 52 minus the ones digit, so it's going to be 52 minus 6, which is 46, which is not divisible by 11, so 526 is not either. About 891, well, again, it's probably not immediately obvious that that's divisible by 11 until you subtract the ones digit from what's in front. 89 minus 1 is 88, boom, that's divisible by 11. And finally, 2002. I can do that one on the whiteboard. Okay, and switch over to that. Okay, so our strategy tells us to take 200, everything in front, minus the ones digit, which is 198. Well, off the top of your head, you may not know whether 198 is divisible by 11 or not. So again, we can do the same procedure over again. With 198, we can take the 19 minus 8, which is 11. 11 is divisible by 11, so 11 goes into 2002. Again, if we're not sure when we get an answer, take the same procedure and do it again. And by the way, as I said, I consider this to be the best divisibility rule for 11 because when I'm working with numbers and trying to find factors, to be able to just subtract the ones digit and immediately have the answer to divisibility by 11 is an extremely cool thing to know. Well, when we look at what we've done so far, in terms of divisibility rules, in our basic session, we had 7 rules. Now we've added on a few more. And what we have now is a complete collection of divisibility rules from 1 through 13. We know the rule for 2, we know the rule for 3, 4, 5, for all the digits right up from 1 to 13. Oh, interestingly, I've not yet mentioned the divisibility rule for 1. Well, I'm pretty sure everybody already knows that. Every number is divisible by 1. And in terms of factors, there's some exercises we're going to do here, and there's some exercises in the practice work that ask you to list like 10 factors of a number. And quite often students leave off what math teachers consider to be the most obvious factors of any number, which are always 1. 1 goes into every number, and also the number itself. So if I ask you for 10 factors of 2002, well, if I was going to do that, the first thing I'd write down was 1 in 2002. Always 1 in the number are always factors. Okay, now we're going to move on to a little bit more practice on divisibility rules with an advanced look. So let's take a look. Compound divisibility rules. So the question here is, let's find the first few factors of 5040. So I've listed the numbers from 1 to 12 here. And so there's one number in this group that is not a factor of 5040. And please let's take a moment, maybe a minute or two even. Which is the one number here that is not a factor of 5040? So let's start applying the divisibility rules, but I'd like you to try that on your own. So I'm going to stop talking for about 60 seconds and give you a chance to go through and try these and see which one of those numbers is not a factor. Okay, it looks like things are moving a little on the slow side here. Okay, someone noted that certainly half of any even number is also going to be a factor. Good call. Good catch. Okay, let's run through these. Is this number divisible by 2? Well, certainly so. It ends with an even digit. Is it divisible by 3? Well, let's add up the digits. We get 9. Yep, it's divisible by 3. Rule for 4 are the last 2 digits, and yes, 4 goes into 40, so 4 is a factor. 5, obviously, because it ends with a 0. Now, today we learned the rule for 6, which was, is 2 a factor and is 3 a factor? And we said, yes, it is, so 6 is also a factor. 7. Well, let's see now. 7. We got 5040 as our number. I'm going to set this up on the whiteboard here. Okay. Again, our rule for 7 is to multiply the ones digit times 5 and add it to what's in front. Now, that didn't help as much, so let's do it again. Yep. 7 goes into 70, so 7 goes into 5040. Okay, how about 8? Does 8 go into the last 3 digits? And let's see, 8 goes into 0 and 8 goes into 40, so yes it does. 9, same rule as 3 again, add it up, adds up to 9, so it's divisible by 9. 10, it ends with a 0. Not sure about that, so I'm going to do it again. Take 50 minus 4, which is 46. I know this 11 is the one number here so far that doesn't work, and let's check that last one, 12. Hey, that new rule we got today on compound divisibility rule said if 3 and 4 are factors, because 3 and 4 are relatively prime, and we've already determined that 3 and 4 work. So of all the numbers there, the 5040, the only one in that list from 1 to 12 that doesn't work is the number 11. By the way, noticing 5040 is also, here's a quick little side fun fact, 5040 is the first number that is divisible by 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There are larger numbers, but that is the smallest number that can be divided by the first 10 whole numbers. Kind of a neat thing to know. Okay, so now we know all these factors of 5040. And so now I'd like you to list 10 more factors of 5040. And that's worthy of your time in the chat box. Now, the information here says, using the information from the last page, that is, which of these are factors, and that's 1 through 10 and 12. And the relatively prime property, list 10 more factors here. Note that there are 48 more. 5040 is also an interesting number because it has 60 proper factors and making it a really super factor-rich number. So, can someone tell me a number that goes into 5040 that we have not talked about so far? I mean, of all the choices here, there are all kinds of combinations here of relatively prime factors. So, what do you think? I got space for 10, but and right now I'm just asking you guys for 1. And let me, using the information from the last page and the relatively prime property, list 10 more factors of 5040. Okay, certainly we could put in 1 and 5040. As I said earlier, 1 and the number are always factors. Those I consider a bit on the cheap side, however. Let's see if we can come up with something a little bit more interesting. And to tell you what, I'll get things started here. So when I look at this list of numbers, they're factors of 5040. I note that like 5 and 7 are relatively prime, so 35 is a factor. I also note that, 6 and 11 are relatively prime, so 66 is a factor. Another group that works really nicely, 2, 3, and 5 are relatively prime. So 2 times 3 times 5, 30, is a factor. Get the idea here? Again, find any 2 or more relatively prime factors, and their product is guaranteed to be a factor of the number we're looking at here. So I see someone said 60, and how do we get 60 out of that? Would be the rule for 5 works and the rule for 12 works. Good. So, and 3, 4, and 5. Lots of ways to approach it. Good job, Jocelyn. Any other? Well, let's see. How about, 9 times 7, 63 is a factor as well. So this is the way, once you know these baseline divisibility rules and this compounding feature, finding factors of a number becomes a very, very straightforward process. And until you know these divisibility rules, it can be an extremely time-consuming and, quite frankly, a very frustrating time for students, because they don't have, without the divisibility rules, they don't really have the tools they need to do the job at hand. So with that, thank you all very much for being here today. The PDF in the comments down below has a chart that has all the divisibility rules from the basic session, all the divisibility rules from today's session, and a page of some practice exercises. And if these divisibility rules are new to you, which I assume that many of them are, it'd be a really good idea to download that package. There's only one page of exercises, but 2 pages of charts that will help you to remember and reinforce these ideas, because, as I said at the beginning of this video today, the ability to break down numbers by factors is something that pervades middle school and high school math. And students who get this under their belt early have a much easier time, and dare I say it, math can actually be fun when you have the tools that you need to do the job. So, again, thank you for joining us today, and we'll see you again for the next session of the Mathnasium Schoolhouse.
It's afternoons that seem to be the most hectic for us, so it was much more convenient when we found Mathnasium at home.
All right, so how do we do half of 5? I think one of the best things about at home is that it really feels like you're almost at home with the student in their house teaching them.
I'm in my comfort zone.
You can just ask for help and the instructor will come right to you.
With Mathnasium at home, I know that they're getting the help that they need.
Awesome, great job.
Mathnasium, changing lives through math.